Hello everyone, this lecture is about strain and strain rate. In the previous lecture, we have discussed about the concept of plate tectonics. So we know that the surface of the Earth is fragmented into different plates, and along the plate boundaries, there is deformation taking place over the geological cycles. These different plate boundaries exhibit different styles of deformation. For example, we've discussed a lot about the mid-ocean ridges, and this map showing you the age of the oceanic lithosphere shows you that the material here is generated, so it has an age of 0, and it cools down away from the ridge. So the Earth is active, the plates are moving. We've discussed about the interior structure of the Earth, and we've introduced the different shells and the thickness of each of these shells. And this knowledge we also know from seismology. So we know that seismic waves travel through the Earth, and the seismic wave, they arise from elastodynamics. So in a way, now we get into the topic. The waves are emitted inside the Earth by, for example, an earthquake, hypocenter, and the waves are traveling inside the Earth, and they give us information about the interior of the Earth. But for this phenomenon to take place, we know that the Earth should be elastic. So the seismic wave can only travel if the material is elastic. But on the other side, we've discussed the motions of the Earth on the geological time scale. And we know, for example, if there is a ridge here, we know that material is being upwelled and that the mantle below is convecting and probably also driving the motions of plates down in the subduction zone and the upwelling of material in the ridge. So for this to happen, the material should be also viscous on the long term to allow convection to take place. And on the other hand, that's an overview now of the surface of the Earth. This is a map of the strain rate invariant. So in the lecture later on, we will define what strain rate is, but for the moment, bear in mind that the red color is indicating you the location of a deformation that takes place faster than in region where the color is in green. So this is fast deformation, and this is relatively slower rate of deformation. This map is very interesting because it shows you that fast deformation naturally occurs along plate boundaries. This is to be expected. But you can also see other domains. For example, here in the India-Asia collision, you have colors here and you have intracontinental deformation taking place in this region, also here along the Andes. So you see fast deformation rates along each plate boundary and also a little bit inside the continents. For deformation to localize at plate boundary, the rocks should be plastic in order to localize deformation. So in a way, we have some requirement now. It's that the rock should be elastic to allow seismic wave to travel through the Earth, but the rock should also be viscous on the long term because we need to explain the deformation inside the continents and the deformation of the mantle, which is convecting below tectonic plates. And the rocks of the lithosphere should be plastic in order to promote localization of deformation at plate boundary. So in terms of what we will call rheology, the Earth should be a viscoelastoplastic medium. So it should cover the whole spectrum of behavior with regard to deformation. And so we need to study how the lithosphere deforms and how deformation affects the lithosphere. And for this, we need two items. So first we need to discuss the principles of strain and deformation kinematics, and then we can discuss how stress relates to strain or strain rate, and we will discuss constitutive models. So for today, we will discuss the first item, we will discuss strain and strain rate, and in the next lecture, we discuss about the second point. So let's start with strain. So we ask Google what strain means. There are many definitions, and you should look at the item which is labeled physics. So Google says that the strain is a magnitude of a deformation equal to the change in the dimension of a deformed object divided by its original dimensions. So what does it mean? What you get out of this? You get out of this that it is a relative change of length. And what relative means is that it is a change of a length divided by the initial length, the original dimension. So you can already imagine the unit. It's going to be the unit of a length divided by another length. So let's consider a uniaxial strain. So there's going to be one bar here. It has an original length Li and a final length Lf. So it is stretched by delta x at the edge here, such that the final length is Lf, and it is equal to Li plus delta x. So we are going to stretch the bar here. Now we make the relative change of length. So we take the final length minus the initial one divided by the initial one. And this is delta x divided by Li, the change of length divided by the initial length. So let's make a little diagram with this. On the x-axis, you have the position. It is in unit meters. We report the length Li, the initial one. On the y-axis, we will introduce something which is called the displacement. It will be the change of position. We call this ux, and it also has unit meters. Here, in our example, the minimum displacement will be on the edge here. It's not moving, and the maximum displacement will be on the edge to the right. Well, it will be equal to delta x. So let's report this on the diagram. Minimum value here, this point is not moving. And this point there will be moving up to this position. So the maximum displacement located at Li in the original dimension is located here at the end. Now we will make the assumption that the displacement is a linear function, so it's distributed linearly along the bar, and that the distance Li is much larger than the displacement delta x, the maximum one. So we have a linear function. We compute the slope of this function. So we take this point, the vertical coordinate, delta x, minus this point, 0, divided by the x coordinate of this point, Li, minus 0. This is delta x divided by Li. Since it's the slope, it is also the derivative of ux, the function here, with regard to x. So dux dx is equal to delta x divided by Li. It is a change of length divided by the initial length. So when I need to mention now that what we discuss are small strains. So in the next slides, we will consider that delta x is always much smaller than the length Li. So delta x divided by Li is much smaller than 1. This is a small strain approximation. it's important to be mentioned now. So let's quickly discuss the elongation now. Remember, we have a 1D bar. It is being stretched. du dx is equal delta x divided by Li. What is the unit of the strain? This is unit meter, this is unit meter, so strain has no unit, it's unitless. It also means, if you make an application here, if the final length is 10.2 meters and the initial length is 10 meters, the uniaxial strain here is 10 to the minus 2. You can recompute it if you want. Now let's consider a 2D case. So we move to 2D coordinates, x, y, and we have a rectangle here, which is being stretched into another rectangle. So we have two lengths, two edges that are changing size. Lx final is Lx initial plus delta x, and the same applies for the y. We will call this the normal strains. They are proportional to the change of shape along each dimension. So how many normal strains would we have in 2 dimensions? There would be one strain along x and one strain along y. Let's formulate them. du dx is delta x divided by Lx, the change of x as a function of x, and duy dy is delta y divided by Ly. Now we have another mode of deformation that we can introduce, and this is now the shear strain. The shear strain, it's related to the distortion of the material. So if we start with a rectangle and we change it into this shape here, what happens is that we will have an angle of shear. So we have a change of of x as a function of y. So dux dy will be equal to delta x divided by Ly. So if you make the trigonometry here, we have the angle theta, we have the edge here delta x, and you have the length Ly, the initial length. It has not changed from the start to the end. So the tangent theta is delta x divided by Ly, and if we make the approximation, it is a small angle. Theta is equal to delta x divided by Ly. So dux dx is approximately theta. The same would apply if we shear in the other direction. Now we shear this rectangle into this shape. We have an angle for the shear, which is here. The facing edges as a length delta y. duy dx, so the change of uy with regard to x, will be delta y divided by Lx, and it's approximately the value of the angle. So we have different modes of deformation, and how do we compile everything together in a convenient manner? We've seen normal strains, we've seen shear strains, and we need to get everything together. And for this, we will use an object which is called the infinitesimal strain tensor. So we are still in the small strain approximation. And this will look like this. It can be expressed as a matrix, but it has the property of a tensor. We have different components here in 2 dimensions, epsilon xx, xy, yx, and yy. This one, epsilon xx, is a change of ux with regard to x. This one highlights a change of ux with regard to y. That one is a change of y with regard to x. And the last one is a change of uy with regard to y. So with this object, we can store the 4 modes of deformation we discussed just before. In general, it is expressed this way. So epsilon ij, this is an index notation. It is equal to 1/2 of duy dxj plus duj dxy, where u would be the displacement vector. So these are partial differentials of the displacement vector with regard to the coordinate. The good news is that this infinitesimal strain tensor is symmetric, such that epsilon yx is equal to epsilon xy. And therefore, we can also write it this way: epsilon xx and epsilon yy on the diagonal are the normal strains, and we have epsilon xy as an off-diagonal term, and also at this spot, these are the same values. The matrix here representing this tensor is symmetric. So in 2 dimensions, you have 3 independent components. If you move to 3-dimensional case, you will have 6 independent components. So you have 9 entries, but symmetry applies. All these terms are equal to all these terms. So we are discussing about small strains. So small strains means that the norm of our deformation tensor is much smaller than 1. So that's where the infinitesimal strain tensor remains valid. And that's, for example, in the case of wave propagation, because the elastic deformations are small, large enough to allow wave phenomenon, but these are small deformations. When you move to structural geology, you have visible strains in the rocks, and to describe these patterns of deformation, one cannot anymore use the infinitesimal strain tensor, and one rather need to use finite strain tensors. Finite strain tensors are one additional level of complexity. Here I show you just one example in 2D of a Lagrangian finite strain tensor. It also is formulated as a matrix here, but you see that the components of the tensor include a nonlinear term. So we have this initial term, which is the same one as the infinitesimal strain tensor, but there is an additional nonlinear term where a product of partial derivative occurs. So that is the kind of finite strain measurement that can be used to quantify visible strains. There are many ways to formulate finite strain tensor, or to quantify it, and this will be the topic of another future lecture. So let's go back to our small strains, and now I want to mention that the deformation in general, it can be split into 2 parts. One is the volume change. So we will talk about a volumetric strain or a divergence. So let's go back to our rectangle, and now we are going to make a deformation such that this rectangle is going to change size. So here the shape does not change, but the volume changes. We keep the same shape, but we change the volume. This is a volume strain. This can happen, for example, when there is a reaction or a transformation of the rock. So for example, an eclogitization, which is a densification reaction. This triggers compaction. The rock is changing volume. It does not imply a change of shape. It's also the case for pressure wave. So when a pressure wave travels in the air or in a rock, it is locally compacting the material, so making it denser, and dilating the material, making it lighter. Of course, with a very tiny change of density in that case. The second type of deformation would be the change of shape. So now we start with a rectangle with a long axis, which is horizontal, and we compress it, and we obtain a rectangle which has a long axis, which is vertical now, and it has exactly the same volume. So with this type of deformation, which we will call deviatoric strain, the volume doesn't change, but the shape does change. So there are different types of deviatoric strains, and this, for example, will be a pure shear deformation. So it means that we only involve normal strains. In this example, you would have one component of the strain, horizontal, normal strain horizontal will be balanced by the vertical strain. So only normal strains, no shear strain are involved to explain this change of shape. And there's also no volume change. So this can happen in the rocks. So sometimes you see flattening in some rocks. It means that the rocks have been undergoing some pure shear component of deformation. Another type of deformation would be changing our rectangle into this shape here. So it means that we apply a shear along an axis. There is no volume change and there is a change of shape. To do this, we involve the shear strains, and remember, these are derivatives of displacement, for example, ux with regard to y. So here you change the displacement ux with regard to y. So ux here is 0, and ux here is maximized to explain the change of shape from here to there. So ux varies with y, and there is no variation of uy with regard to x. In this example, it's the opposite. We change the rectangle into this shape here, and there is a maximum displacement in y that varies along the edge in x. So it will look, it will be symmetric. So remember, the strain tensor is symmetric. So this change of shape and the one we saw on the slide before result in the same infinitesimal strain tensor. Another example of simple shear deformation is, for example, sheared trilobites. Of course, these involve finite strains now, so it would be, it's not justified to study them with an infinitesimal strain tensor, but it's just to give you an idea about the application of these to geological examples here. You see a trilobite that you can, for example, observe on the field. You collect it and people try to correct the shape. So you can quantify the deformation that the rocks undergo or underwent by correcting the shape of a trilobite. So initially it's like this. It means the rock has suffered this deformation during its history. So in general, both shape and volume changes take place during deformation, so we need to keep track of them, and that's not the simplest task. So how to keep track of both the volume change and the change of shape? We are going to introduce a measure, and that is the trace of the strain tensor. So the trace of the strain tensor, it means the sum of the diagonal components, will be called the volumetric strain, epsilon vol. So that's what will represent a change of volume. So we want to filter the change of volume and the change of shape, so we can create this object, and this we call the deviatoric strain tensor, and it is measured by subtracting the fraction of volumetric strain from the total normal strains. So what does it mean? It means that to construct the deviatoric strain tensor, we are going to remove 1/3 of the volume strain to the diagonal components. So we only change the diagonal components. This is how to create the deviatoric strain tensor. So it can be formulated this way. Epsilon dev is epsilon, the total strain tensor, minus 1/3, the mean of the volume strain, basically, times delta ij, where delta ij is the Kronecker symbol. In 2D, it's a diagonal of ones. Now, I introduce the strain rate. So in geoscience, the deformation, it occurs over long time scales, and many processes are actually time dependent. So we consider the rate of strain. Remember the map with the rate of strain. This is showing you the amount of strain per unit time. So what's the unit of a strain rate? We have strain per unit time. Remember, strain has no unit and time has unit, let's say seconds, for example. So it can be 1/seconds. That would be the characteristic unit for strain rate. So the strain rate is nothing else than the time derivative of the strain. So if we have epsilon on one side, we take the time derivative and we have epsilon dot. In the following, we'll make the assumption that the time increments are small enough and the changes of strain are small enough. So we will approximate the derivatives by a ratio of changes. Let's look again at our 1D example. Remember, the bar is being stretched from initial to final length with, and now we consider that this is taking place during a time increment delta t. So we take the elongation, but we take the time derivative of it. So let's make delta strain divided by delta t. So we take the final strain minus the initial strain. The final strain is delta x divided by Li minus initial strain is 0, divided by delta t. So delta x divided by delta t divided by Li. So that would be the strain rate in our example. The strain rate is also a tensor in general when you move to 2 dimensions or 3 dimensions, and it looks the same as the infinitesimal strain tensor we introduced earlier, except that all components have a dot, an over dot. In general, the components are expressed the same way. You see epsilon dot ij is 1/2 now of dv I dxj plus dvj dxi. So now we have v. And what is v? V is no more the displacement, but it's the velocity. And what is the velocity? It is the rate of a displacement. So v is the velocity vector here. The good news is that the strain rate tensor is also symmetric in most cases, such that epsilon dot yx is equal epsilon dot xy. So in 2 dimensions, these are 3 independent components, and in 3 dimensions, it's going to be 6 independent components. The same rule will apply to study strain rate. it can be split between deviatoric strain rate and volumetric strain rate. So one can always compute the deviatoric strain rate out of a total strain rate by subtracting the volumetric strain rate, which is the trace of the total strain rate tensor. So that's to show you now the map again. So this is a quantification of the strain rate along plate boundaries and inside some of the continental domains here. You see that this is an important measurement. It's giving you the intensity of the rate at which deformation is taking place. So as a conclusion, the strain tensor and the strain rate tensor, they allow you to quantify the kinematics of deformation. So one is giving you the amount of deformation, and the other one is giving you the rate at which this deformation is taking place. The deformation leads to change of shape. These are deviatoric strains, and they can lead to a change of volume, and these are the volumetric strains. The deformation, the strain tensor or the strain rate tensor, they can be split between volumetric and deviatoric parts. Now that we've introduced strain and strain rate, we can, in the next step, discuss the stress and build the relationship between stress and strain and stress and strain rates. Thanks a lot for your attention.